Hi, I'm Jeremy Hare. I'm a postdoc at NASA Goddard Space Flight Center, and I hope you had a chance this morning to review my slides. I apologize. No worries. Anyway, I'm here to talk about Magnetar for you, a 142 from infrared hard X-rays. And this work in collaboration with Bettina, as well as some other of my collaborators in the US. Just some basics about this Magnetar. It has a spin period of about 8.7 seconds, magnetic field on the order of 10 to the 14, and characteristic age about 70 kiloyears. Like most magnetars, its X-ray luminosity is higher than its spin-down luminosity. The distance is about 3.64 parsecs, and it's infrared bright in the sense that it's one of the brightest magnetars at infrared wavelengths. So previously, Spitzer observed this source in 8 micron, 4.5 micron, and 2.2 micron with CAC videos. In this group, Wang et al., when combining these infrared observations with optical data, found that there was this infrared excess, which you can see the bump here. So they also, you'll notice here, these triangle points are the observed points, and they de-redden them using an AB of 3.5. And you see there's a power law component here in the optical, and then there's thermal bump here. Furthermore, they observed with Spitzer IRS spectrograph, and the data quality wasn't great. They found this hint of an excess at 9.7 micron, which they claimed was a silicate feature. And basically, the picture that kind of came out of all of this was that this is potentially a supernova fallback disk that was around this magnetar. So that was the model they came up with to explain this excess. The infrared data were fairly well fit by a dust disk model with a temperature of about 1200 Kelvin. So these supernova fallback disks are really important for pulsar evolution and magnetar evolution because they can act on the pulsar and slow the spin down. And they can also potentially vary magnetic fields and things like that. So they're very important to understand. So we wanted to try to get a better constraint on this disk. So we proposed to observe it with the James Webb Space Telescope. Here at the bottom, showing the filters for the program that we proposed. And we used 2 detectors and 3 observing modes. First, we used the Hare low resolution spectrograph. And then we had a near-cam imaging campaign along with a near-cam timing campaign. These were all taken in succession. So just a big warning, Webb is very new still, and they're still calibrating a lot of things. So all of these results are subject to change. We got the data in September 2022, and I think it's already been reprocessed 3 or 4 times. Most of the reprocessing now is minor changes and things, but some of the earlier ones made big shifts in the data. So I thought I'd spend a little bit of time just explaining the data products that we get out of Webb, since it's a new instrument and how much people have seen. So for Hare and the low resolution spectrograph, we basically have to take an acquisition image to locate the target and place it in the slit for the spectrograph. So this is the Hare 560W filter image. The source is down here. And basically this little line you see here is the slit. So they basically line up your source with the slit to place it in the slit for the spectrograph. Once they do that, they take 2 observations, which are called nods, where they place the source at different locations on the slit. And essentially they do that because they take 1 observation where the source is placed at the top and the rest of the chip is more or less blank, and they place it at the bottom. And they do that because then they can use the first observation to subtract the background from the second observation. So that's what you're seeing here. Basically, they did these 2 nods and then subtracted the backgrounds and then combined them. So basically, this is your source spectrum here in the middle, and these deficits are because the background was subtracted where the source was observed previously. So this is what's called the 2D spectrum. You know, the long wavelength end on the left and short wavelength on the right. And you can notice the noise gets pretty bad at the longer wavelengths. And this is due, I think, to the thermal background of the telescope. Oh, I also wanted to point out there's this hot pixel here, which you'll see in the 1D spectrum. Just keep that in mind. So once you extract your spectrum from the 2D spectrum, you get this 1D spectrum, which is shown here. The hot pixel that I just mentioned is here. And notice now that the wavelength's flipped. It's just the way the data products come. So the source ranges between about 30 to 70 microjansky. You see this curvature here. Come back to it in a minute. So NearCam actually observes in two filters simultaneously, a short wavelength filter and a long wavelength filter. We chose the 140 and 250M filters. These are the images here. And so you see the source is significantly detected. There's this banding that happens in both filters. It's just easier to see here due to the readout noise from the detector, and it can make your backgrounds fairly complicated. You see some excess emission next to the source due to this banding. So using aperture photometry, we basically extracted the fluxes, and plotted them with the mirroring spectrum, and this is the picture we get. But you'll notice the strong curvature, and if you remember from the first plots I showed you, this is due to the reddening, because this is just the actual observed data. So we need to apply some de-reddening, which we do here, and we use a similar value to what was used in the Wang et al. Papers, 2006 to 2008. You see this has a tendency to raise your points up, and notice that there's this dust feature here, which is common in infrared observation, which gets corrected by the reddening. So this kind of weird dip. So once we have our de-reddened photometry and spectrum, we can start using models to try to understand if it's thermal emission or power law emission. So just in the mirroring spectrum, the black body model does not fit very well. So this temperature here is low, it's like 580 Kelvin. So compared to what they found, which was about 1000 Kelvin, we would need to push the peak of the thermal emission to higher wavelengths, and it makes the model even worse. So we do find that the power law fit works much better. Again, alpha spectral index is about -1. And then combining that with the NearCam data, you see that goes to the points fairly well as well. And this red line here is showing this is just placed at 9.7 micron, which is where they saw evidence of this silicate feature. But we also don't see much any evidence for a feature there either. So basically, in conclusion, or for this part, in conclusion, we find that there is a power law-like spectrum with no evidence really of a disk. The infrared luminosity is on the order of 10 to 31. We don't see any evidence of silicate feature either. So we're currently trying to work on the Spitzer data and reanalyze that and try to figure out if something actually changed or if something was misinterpreted in the Spitzer data and there wasn't actually a disk. Concurrently with the web observation, we took a nicer NuSTAR observation. So here I'm just showing the NuSTAR data. So this is the unfolded NuSTAR spectrum, and it's been suggested previously that perhaps the hard power law component that is shown here could extend down the infrared and be due to the same emission component from the magnetosphere. So there was a previous observation that was reported by Tindulkar, and they found a photon index of about 0.3. Our new one gives a photon index of about 0.5, and this may be due to some calibration differences since this was taken very early in the NuSTAR mission. So we're still looking into that. In either case, the extrapolation of the mirrored data basically provides too low of a flux. So the near infrared component has to be going from something other than the Hare. So lastly, I'll talk about NearCam timing, which has unfortunately had some technical difficulties, which if you buy me a beer later, maybe I'll tell you about. But essentially, so far we don't have NearCam timing data in hand. It's scheduled to be reobserved later this year, probably in the fall, when the observing window opens back up for the source. And this will allow us to search for pulsations at near infrared energies to try to understand if it's coming from the magnetosphere or not. And we're also going to reobserve with NICER and probably SWIFT. So we'll have concurrent X-ray data and compare the pulse profiles and relative phases of the pulse peaks between the two. And this plot here shows the filters we're observing in for NearCam timing and respect to the data that we already got. And just for those that are curious, NearCam's timing resolution is as good as about 2.25 seconds. So we'll be able to get a large number of phase bends for this pulse since spin period is so long. Okay, so I'll just leave my summary slide up here and take any questions. Thank you.
Do you have any questions? Yeah, I have some two questions. Got very great talk. So the first question is, at least for radio magnetar, we always see them to have, not always, but some of them to have a spectral index changing over time. Have you ever seen that in higher energy regimes?
Yeah, so at least there's that evidence between this and New Star. So I need to go back and check to make sure it's not just a calibration thing. I don't know at the moment whether it's an actual change or not. But that's one of the reasons why we wanted to observe simultaneously with New Star and Webb. So that if there is any change, we kind of get rid of it.
So the second very quick question is, do you think it's worth it to try to observe that in millimeter wavelength?
Probably.
This one might be too high for Alma, right? So
Yeah. Yeah.
it will observe. Oh, sorry.
Thanks. Any other questions?
Yes, sir. So a slightly naive question, I think, but so how much of a disk could you hide in there?
It's a good question.
And I'm thinking mostly of the spin evolution and how much mass would be in it.
Yes,
they thought this one through.
They do this estimate in the line paper for the spin evolution and mass. I don't remember the numbers off the top of my head. I know that the radii, so I haven't fit like actual disk models yet. I was just using the black body, which if you look at the Wang paper, they just get a slightly lower temperature when they do that. So I don't have an actual disk radius, but at least in the black body radius, it's like a couple hundred, just already got to.
So just to the question, if the disk was 300,000, you just detected in your data, right?
Sorry?
If the disk was cooler, you wouldn't have detected in the vision horizon.
It was much cooler, yeah. So the best fit we get now is like 500-600 Kelvin, but you see that's like, it might still be detectable there, but much further, yeah. Yeah, yeah.
So there was also this inside 24 MIPS observation, so even longer wavelength. And there was, a hint of detection there, but it was not super significant. That long wavelength.
Yeah.